This presentation is on the design principles and construction of district geothermal systems by presenter Cary Smith of Sound Geothermal Corporation. Cary's other title for the presentation is Community Geothermal Systems, the Thermal Energy Highway. So we'll go with that. This was presented at NY-GEO 2018 in Albany, New York on April 18th, 2018.
Hi everybody, we're about to start the last session of the day. So if you can please be seated, we'll be passing around the sign-in sheet shortly to get PDH credits. This is a 1 credit course. So please sign the sign sheet. Introducing our final speaker, Cary Smith from Sound Geothermal.
Thanks, Bill.
Cary's been a leader in this industry for a long time. Really fortunate to have him here today to speak to us. Cary, I'll leave it up to you.
Okay, thank you. Well, good afternoon, and we move forward. The air conditioning is good up here too, and we'll go through. But you know, if you have any trouble seeing some of these slides, there's plenty of room up here. I'm kind of just to give you a little bit of background and stuff. My original conversion into energy was as an oil and gas guy, drilling engineer, project engineer, and so forth. And then back in 1997, I was introduced. We did some intermediate work in high temperature geothermal, Phelps mobile stuff. We invented a system that goes 600 degrees to, you know, at 16,000 feet. But little stuff that we did. But anyway, somebody said, "Hey, I know these guys that heat and cool with geothermal water." And of course, being on the oil field, my answer was, "But yeah, right. Let's figure how in the heck do they do that?" So I made a presentation to came back and went to Sacramento to one of the conventions, listened to the people talk about this. And what they were talking about was heat pumps, ground source heat pumps. And literally became so enamored with the technology and what it looked like we could do. So the background of the ground and so forth, and the different components that go into it. Of course, hydraulics is a big thing in the oil field. And transport energy. That's all we do. We produce and transport energy and stuff, and every once in a while we'll consume it as we go through. So it started into a whole new career and a whole new outlet. So Sound Geothermal was formed. We went into it, and over the time we started using our kind of can-do attitude. We worked 7 days a week, 365, 24 hours a day in the oil field. And holy cow, I now had Sunday off. Pretty good deal, you know. So this is a promotion. What they just didn't tell me was that you don't get paid for it. So I'm coming in here. Hopefully, I can kind of keep you away a little bit and entertain you a little bit with what we're doing. We're going to talk about some key principles about taking GEO to the next level. And it's not new. It's been done before. We did our first district system in 2002. So that's 4 years out of being oil field trash, you know, and stuff. And when people ask me more about that, you know, I told them I'm atoning for my sins now in green energy. So you know, for all the raping and pillaging I did in the environment. But the truth is that this is really a key technology, and our cities need this. Our landscape, our people need it. So the carbon reduction program in New York State has come up with has just been really tremendous example for the rest of the U.S. And there's a lot of other states that are kind of starting to struggle behind you. Fortunately, Utah's not one of them. But we'll see. We still like that oil and gas. So this is an AIA certified course, health, safety, and welfare. You've got some objectives that are pretty much there. I'm not going to go through those. If you're a PE, you need to sign the sign-in sheet so you can get the credits. But what we're going to talk about today is we're going to be talking about concepts of energy and how we move, and in particular, how we can turn around and do something that no other HVA system that I know of can do. And stuff, and that's a heat pump system that can move energy, store it with a little bit of borehole help or some other type, and then reuse it somewhere else, all for less money than what we started and at a higher efficiency. So when we start taking the principles, and I understand you had Steve Kavanaugh go through it, acting with you guys this morning and stuff. Steve, I've known for a long time. I'm going to honestly say he was kind of one of my mentors for 2 or 3 things that he's taught me that I consistently use. The first one, pumping is forever. So when we're talking about systems, we're talking about what we're doing. You got to pay attention to how you design it, what you're doing, and where we're going with it. So inherently, what you're going to see here is that we've adopted a one-pipe system. And a one-pipe system is basically a hydraulically independent circuit. It might be a building, or a room that's several heat pumps, or even a whole campus and stuff. And then we turn around and we utilize, as things come on and off that, we have a separate hydraulic circuit that we feed. And I'll show you and explain to you how that all works. And so, but these are the key concepts to what we're doing and what we're trying to do, because we're minimizing at that point pumping energy if you're careful in your design. So anyway, is this new? 1948. That happened to be my 50th wedding anniversary present to my parents. They were born October 25th, or they were married October 25th, 1948. Okay? So and it's really kind of an interesting magazine. Not that it has this article on ground source heat pump, but this actually has ads for cigarettes and alcohol. Big deal. And then nice ladies in fancy dresses with gloves on. What you need to start with here is the concept that heat pump efficiency is really kind of the focus of it. The key designs you're looking at. It can be flow. It can be temperature of the fluid and the flow rate of the fluid. And so these are the key points that you have to remember. So if I balance and manage these correctly, what's going to happen is I'm going to keep my heat pumps happy. And heat pumps being happy means COPs in the upper ranges above 4, EERs above 20, and so forth. So you turn around and for management, but also the big thing about it, what killed this market, this heat pump market in the 80s, was lack of attention to detail, and the fact that we had a bunch of heat pumps that were pretty much set in a very narrow range, 55 degrees up to about 77, 85 degrees. Got above that, they started blowing compressors. Got below that, they just went down on low head. Jim, you've done that, right? Yeah. Seen that? Seen been there, done that? School districts that used to have it, and then you turn it over to an inexperienced maintenance guy. And all this stuff goes to heck, and pretty soon they're tearing the system out. They want to do something different. Remember, a water source heat pump, a boiler power system is a water source heat pump. A ground source system is a water source. You put the two together, you got a hybrid. But some of the things, the other things that we really want to look at, and is patterns of what we design for and how systems operate. And if you take away nothing else from this presentation, even if you're headed to the bar, you really might get something out of it. The point of this is that 90% of the operating hours of the year, it will take less than 50% of the load of the building. Now, what does that tell me about sledgehammers? Non-controllable devices, non-VFD devices. What does it say? It basically says, hey, listen here, if you pay attention to this, and this is true through the temperate zones of the world, not just the United States, not just New York, not just Utah, even works in Florida. That's Joe. He's out there. Well, the Germans took it one step further. This is a function of what basically is their German Energy Star, what they were looking at. It's called the Blauer-Engel rule. And it breaks it down even further. It brings me integrated spots that I can start to look at. If I turn around, I'm going to be at 100% flow or 100% load in the hydronic system 6% of the year. I'm going to be 75% load 15% of the year. Look here, 50 and 25. And look at 25. So what does that indicate to you about devices that we have out there or systems we have that we can turn off or slow down. So we talk about an integration. This is kind of a nice place to suggest to you, this is an integration method we might be able to use to rate all equipment at these particular points. And you'll hear later, maybe somebody's going to say, talk about what we're now calling lovingly ICOP/kW per ton. And it means we're going to take the whole system, we're going to put it together, we're going to crank it out, we're going to measure it at different points. But those points are the same for every piece of equipment out there. Furnace, two-step unit, VFD, VRF, doesn't matter. Air source. Because all of a sudden, it doesn't matter what the temperature is. It matters about where you perform during that percentage of the year. So think about it. Now, energy loop, water loop. What is it? That's where we're harvesting, moved, and reused. A pipeline is an energy highway. We want to use that term. Somebody said I shouldn't use it. It applies on driving cars down there, so wasting gas. But the truth is, I need a transport system. Air source doesn't do that. The air is not a good transport system for me to turn around and take multiple devices. However, in any water-based system, I can take multiple devices, put them together, and I can, as you know, cool in one spot and heat in another spot. And it's basically the same energy. How much energy did it take to move that? The question. Amount of pumpage, right? Pretty much. That's a differential. Because it was going to do something to heat and do something to cool anyway. When I put them together, the only thing that helps, the only thing that penalizes me against that system is the pump energy. So, heat pumps cooling, add energy to the loop, heat pumps and heating, remove energy from the loop. Okay, we're going to use this here. Now we're going to start to multiply on it. We're going to start to build on it here pretty quick. Okay, what can we do with this? We can move energy from one building we're used to another. We can use it for ground or thermal storage. By the way, when we start talking about these systems, all of a sudden our boreholes are not necessarily boreholes that are looked at in number of feet per ton. They are a thermal storage system. And it needs to be looked at differently. It means I can shift load, move load, store load. All of these things that I couldn't do with the air, or a boiler, or a cooling tower. Solar thermal energy. Holy cow, what would happen if we took solar thermal and took the solar fraction from 65% to 100%? Pretty soon it's constant. You don't believe me? Google Drake's Landing, CA, Canada. It's Drake's Landing Solar Community, but DLSC.ca. Start looking at that, and they've got a focused solar array. They store 160-degree Fahrenheit water in the ground, and they use it in the winter for heating. They don't have to, they're in a nice spot in Canada where they open the windows for cooling. But they use thermal storage and thermal fixing. The starship thermal storage and borehole thermal storage. And that's the key to the system where you start seeing solar fraction, 100%. And it seems to do some of the stuff, if I just make a conside comment about PV, if you size your PV array, you size it not to sell it back to the power company, you sell it to use. What are you going to use all the time? Anything above that's wasted. Because you're not getting on top economic value out of it. Okay? So, we're going to level the energy loads of the system. Holy cow, what does that do? Shift system electrical demand peaks. Shed excess energy at a time of day that's most advantageous for you. Store energy to sell other users. Microgrid applications. That thermal energy is sales. And in some places, so is the carbon reduction. And we can increase system efficiency from 300 to 600% over what you originally had. As an example, let's go through this. So, we're going to talk about central loop and hybrid systems. Let's start talking about waste energy recovery. That's what we do when we move it from one place and reuse it, or we store it in the ground. Consider two systems operating at their respective peaks. System, coefficient of performance. This is the second thing Steve talked about. Is always look at the system capacity, the system performance. Forget about the box. You might look at it as an incidental part, but look at the system efficiency. That's what should be driving your decision about how to put a system together, particularly a central loop system. So, we call this conventional flow away energy. gas companies like to slide things up. 2 independent buildings, 500 tons each, okay? And can you all hear me, or do I need this? Yeah. You're fine. Okay. Consider 2 systems independent of one another, both 500 tons. And stuff, and I got an ice plant and a laundry food service. Pretty typical example. People talk about this kind of thing all the time. Okay, both 500 tons. If I were to turn around and calculate the system COPs in there, it kind of tells you the parameters. Like I'm using my system is at kW per tons, about 3, and the EER is about 4 in the boxes. And I take and calculate all my pumps, all my boxes, everything else on this system. I'm going to come up with a system COP, right? And it's going to be good. It's going to be better than one. Why? This is different. Look, come on. Because I'm using compression. A chiller's a heat. Okay? This guy over here, though, he's got this nasty thing called a boiler. But man, it just works. It just keeps going. But is its efficiency going to be greater than 1? No, and it's going to degrade rapidly over time. But if I put the 2 together, just then kind of say, okay, this is my shopping center, whatever have you, I come up with this system COP at 1.17. Slightly greater than 1 because the chiller overrides, the work the chiller does overrides. If I take these independent buildings and simply connect them with a water loop and utilize heat pumps, what happens is what energy have I added? Pumping energy. Pumping energy. Thank you. And how much? Not very, huh? In comparison, particularly to the compression that I'm using here. Yeah, I've added compression over here. And so first I had maybe, but now my compression's greater than 1 here too, but I'm using just regular heat pump. The problem I have is that if one shuts down on Saturday, and Joe wants to work Saturday, he's out of luck, isn't he? He got no place to send his heat. Or vice versa, when the one takes Sunday off and then takes the next Monday off. So what do? We start looking at this. What's the solution? Storage. Oh, by the way, this is your magnitude of the calculator. Got this for the engineers you can take a picture of that for the calculator. So I had another small pump that is connected to what? A ground loop, a thermal storage device. And I'm going to say ground loop out here because I like that, and that's what we're talking about because this is NY-GEO. But we say a 1 million gallon water tank works too. But this is the back where we start looking at it. We start looking at incidental technologies that go with this. And when we start talking about thermal storage, when I run out of making hot water here, where does my extra energy go? For the thermal, excuse me, right here. So now all of a sudden I've got an opportunity. Joe can be down Saturday. Juan can be down Saturday. And stuff. And we can turn around and continue on our operation and not like from this electric, the whole thing. So what I'm proposing to you is that thermal storage systems on a community scale are the next thing we need to move this whole technology to. And we need to start looking at it. What did I do to emissions? We'll see a little bit about here what we do with water and PM2.5s. Just to give you an example, I call this slide heat pump alchemy, and you'll see why in a minute. So I got a 14 ER and a 405 in my ice making plant. I'm just going to make 1 ton worth of cooling, 1 ton worth of ice here and stuff. So my input is 12,000 BTUs, right? Or what I'm taking out of the ice. I'm taking 12,000 BTUs out of the ice, right? Plus a little bit of what? Compressor energy, right? So what happens when I tie it and I take that compression energy at those efficiencies, and it says all of a sudden I multiplied my 12,000 BTUs to 14,666. Magic, you know, this is why we're smoking mirrors, guys. And then we come back here, we start looking at input energy for work. When we went to a heat pump, we gained a little bit. We're using all of the energy. None of it's going up the stack. So what happens is I get another goodie here when I put this and start using compression here. I get another 4,800 plus BTUs to the system. So started with 12,000, add a little pump energy and stuff, which we could have taken out of there. In this case, it'd probably take about what? 20 watts, 30 watts, 40 watts? Not much. And stuff, and I'm up to 18,000 plus. And then the next, there's the alchemy pump. And stuff, what did I avoid? Well, I avoided, if nothing else, the amount of natural gas that I would have had to combust at an 80% furnace. So I'm avoiding another 21,000, I'm avoiding 21,700. Now tell me something, if you think about that, is the true answer to this question the sum of 14,660 and 21,728? Or is it heat pump alchemy? I want to pose to you that it's really not a question, but to look at it. These systems are able to move energy and take advantage of things that we threw away yesterday. Today, we don't want to throw them away. So, central loop systems. What happens when we take that and we start multiplying buildings together? What do? Well, central loop systems have multiple assets distributed across the whole system. And we think of it as a Lego system. So each module, each central loop, or each one pipe central portion of it is a Lego, and it's got pieces attached to it and stuff. And they may be smaller Legos, or maybe, just maybe, it's got a bigger Lego attached to it in another block or a mile away or along a whole cityscape about where we can go. Well, and then in these systems, we technically tend to still have peaking devices in it, so they're still hybrids. We're still seeing a little bit of use of boilers and cooling towers. Not so much boilers, but cooling towers. But the ground source and any place you can find it really becomes a thermal storage issue. So now we've got it, and what we're finding out is when you go through and see these examples, I've got a couple of places where we've applied this. One of them's over 10 years old. That go through. It just seems like the bigger it gets, the more stable it gets, the easier it gets to be controlled, because now if I'm using a one pipe system, I might only have one factor of control to speak of primary fit. That's the temperature of that fluid. The next thing I change would be the flow rate. And sometimes that becomes counterintuitive when you start to manage these systems. Sometimes what I want to really do is just not have a hot spot. Unlike a chilled water loop, I speed my pump up. So I'm getting more distribution faster and stuff, and I'm not getting as much because obviously what's going through the central loop is much greater than going through any one of the parts. All right, central loop's assets, what can they contain? Ground loops, open loop systems, renewable assets, solar PV, solar thermal, wind, cascading high temperature geothermal. That's one we miss a lot. And so we've got a whole bunch of places across the United States and other places where we can get 120 degrees out of the ground, 125, 160, 170, 180. Not enough for power. But it does make some sort of sense when you start looking at tying into geothermal here. I'm getting ready to go to Tibet, Alasha. We have a geothermal system. We're permitted to, the group that we're going with has a permit for 85 kW, high temperature geothermal. We're talking about taking the excess heat down to the city and stuff, and trying to figure out how to keep them from burning the wood. Okay. Combined heat and power, CHP. Wendy's, back in the power stream. How many people were old enough to remember that we had power battle going on in the United States between one side of the U.S. and the other about rates? You know, we're transporting energy to California, who was getting electricity at 36 cents a kW. And if you went in an REA in Montana or Utah or Wyoming, where I was, we were selling all our excess power for about 4 times what we were paying for it and stuff. So at the end of January, we either get a free month or we get a nice check. And the biggest check I got was close to $1,000 on my home. And that's how much the REA was kind of making the whole thing. But when we start talking about combined heat and power, what's the major problem? I have to have a dedicated building to take the heat, or dedicated spot to take the heat. What happens if in the wintertime in particular, I'm able to bleed it into the central loop, which will raise my circulating temperature, which will increase the efficiency of the heat pumps all the way across campus. Now I've taken an asset that's supplying 1 megawatt or whatever we're asking for, the CHP, and I'm multiplying its effect. I don't have to have steam, I don't have to have a hospital. Summer I could go to an organic Rankine cycle, absorption chiller or something like that. But the truth is that what we usually do in that one is we start to store it in the ground. We start to put it in the ground and stuff, and also the campuses and all these. Wendy's, back during that time, found out that they could turn around and put a CHP unit, a little generator, and a heat recovery. And one about 10 o'clock, when the rates in California started to come up, Southern California, cranked on the generator, pulled the breaker on the main power system, make all the hot water I need to keep the restaurant clean, and all the energy I need at 2 o'clock in the afternoon or 3 o'clock where my peaking goes away, generator turns off, and go back on city power. Average, when we're on regular city power, about 16 cents. Average off city power, 36 cents. How dumb was that now? I bought a generator. I can't start to get the heat. I got to make my hot water, not burning any gas. I'm making all like every Californian in the whole thing happy. Not only my heat pumps, but happy. Anyway, other waste energy recovery. There's other ways to recover waste energy. Biomass, all kinds of stuff. And other central loop system. That's the Lego concept I'm talking about. So, how does that work? And how do we control it? Well, this is a real quick picture. I've used this for years. Some of you have probably seen it before, but it still works. I take and segregate the buildings, or we take and segregate the buildings, so that they work as independent entities. So if I have a heat pump system in this building I'm showing up that has some diversity, the blue and the red, and stuff, and I modulate my temperature inside the building between 55 and 85, kind of a sweet spot for heat pumps. First of all, when I start, you'll notice here, all these are above 32, so guess what? No antifreeze. Big first dollar saving. Okay? And then as I go through this, and stuff, it says, well, what happens if I get out of range? Now, it falls to below 55, it goes above 85. Well, that ain't too happy. So I turn on what amounts to be a small transport pump. In the case of one of my buildings, about 70,000 square feet, that's less than 2 horsepower and stuff. And I start to take energy in and out of the central loop. Well, he's got other stuff on it. And believe it or not, he's set up to do this kind of the same thing. But I give him a little bit of a break here. I can let him go down to 50. But I have a building all the way in heating up here, one down here in cooling stuff. So this guy's turned on the head and heat to the loop. This guy's taking heat out of the loop stuff, and I get the central loop, and I got a thermal mass there, by the way. It's also kind of a nice benefit to me, and everything else. And we just go on with that. I'm unhappy. So what happens if it gets below 50 or above 85? Well, I'm thinking, can I stand this? What I want? Well, heat pump typically 7-degree drop and heating, 10-degree add and cooling. So maybe I'm going to start looking at a cooling tower really at 85. It's like 86, somewhere in there. But the first place I'm going to go is I'm going to go to my loop, because I added another small pump. And I either have energy stored in there or I'm able to receive energy. So I'm able to touch the system. And it may be just enough to keep me from firing a conventional piece of equipment. And historically, it has been, big time. That doesn't work. We get out of range of that stuff and say, okay, now we got to go to the big boys. Remember how much the part of the year is this now? Maybe 6% of the year? Maybe 21% of the year? Is upper 2 brackets? We got the 2 uglies come up. The cooling tower and the boiler. So as you're looking at this thing and you think about the progression and you go back to this part load where I started, the Blauer-Engel rule, the 50-90 rule, and stuff. And I designed the system to operate almost 8,000 hours a year in this combined heating and cooling mode. I took advantage of what I had, and yeah, there's my sledgehammer. These guys over here. This guy's kind of like a ball peen. You know, but it's, in general, that's the fundamental concept of a single one pipe loop and how you control it. I just told you enough to go out and build one. Calculate your pumping energy, calculate your head loss per 100 feet, make sure you do. Follow the rules that turn on, say, you know, somewhere between 1 and 3 feet per 100 head loss. Now, make sure you're pumping on the central loop at this point in time. This is just a side comment. We're not going to go into it deeply. That you start thinking of different configuration for your central pumps. What we found out was with conventional VFDs, we cannot slow the pump down slow enough to truly take advantage of the system. So what we did was we set 3 pumps, each sized for 60%, because I'm in a school or a hospital, these N+1, you know. And what I do is I start ramping the units down, but I do it in a staged effect, similar to my flower eagle rule, so I don't have any hunting. So we took care of some of that nonsense too, right off the bat. When we come back in, we sit this together, we put it together, we started running, and you know, bingo, here we go. And so now I get some pumps, I can get down. So it's not unusual for me to turn and take a 50 horsepower pump and look at it working on a system just hour after hour after hour at 20 hertz. Or slightly under, it depends on what the size of that pump is. And I'm pushing maybe 1,000 tons. So, engineer, do the affinity laws in your head real quick. What I got in use? About 10 horses. Now, does that meet these pump rules? You better believe it. And so, he's right.
How far apart can these buildings be?
Hmm?
How far apart can these buildings be, and how big your central is?
Well, let me see. Our largest spread out right now is probably 4 miles. We have cities, the cityscape we're designing up in Toronto right now that takes into how many city blocks, right?
Yeah.
How many is it? Is it 8?
Distance?
Yeah. About a mile around that loop, isn't it?
Yeah, at least.
At least about 8 city blocks. And then we have those stub outs, like you see here, on this, to move to another loop. It's the next 8 blocks. Over there, the next 8, and it doesn't matter. You see, he happens to be close to a city park, and you've also got multiple. You've got water wells on there. You've got ground source wells. Plus, we got thermal storage, and our big hammer is not the boilers and cooling tower. Our big hammer is the water well. Does pretty much the same thing, but also think about the horsepower it takes to run a water well. So technically, it is my sledgehammer, but we go into these things. So the one loop I'm going to show you today, we've got over 3 miles in it, and 1 college campus. We're getting ready to double. So, and some of the buildings are close together, some of them far apart. Some of our loop fields are as much as a half a mile apart. They're not all in one place. So we distribute them around the loop where we can. We take advantage of open spaces. You'll see that. Okay, what else happens when we start playing with this stuff?
Well, go back to the mic.
Yeah, I can go back to, yeah. Thanks, Bill. Yes, I can go back to the mic, but think what happens here in the water side. 41% of all our water use, potable water use, is at the electric plant. Okay? Anything we reduce on site is going to reduce water use 2 places, site and source. So we're looking at the exergy of the system right now when we start playing with these things. And so I'm proposing that these are also calculations that should be involved in when we analyze the efficiency of the system. On site, 1/3 usually of the site water is often consumed by cooling towers. You know, when in our climate at high school, we'll consume about 600 gallons an hour. In high school, it might be 500 tons. And so that's kind of cycling on and off and everything else. But there's a lot of water in it. Hybrid systems themselves can reduce the cooling tower water by about 70%. Why? Because remember, now I'm utilizing that waste energy that I normally threw away. all right, storing it in the boreholes or whatever have you. The balanced waste energy recovery system is, again, the GHP thermal storage system can eliminate all cooling tower use and water consumption. And we've got systems where we've done that. But, you know, it's a matter of kind of sitting down and doing the math, but it's really unbelievably forgiving. Okay, got a little bit of show and tell here. Colorado Mesa University, South Grand Junction, Colorado. Anybody been there? Been down in that area? Besides, we call it Happy Valley sometimes. Colorado. But anyway, it was a small community college less than 10 years ago. And stuff, and it's absolutely gorgeous. Right on the Colorado, right down by the Colorado River, Grand Junction and stuff. Gateway to Moab and the Grand Canyon and all the other stuff. San Juan Mountains and so forth. But it's just been absolutely gorgeous. And the idea that a very visionary president who used to be the Speaker of the House of the state of Colorado that says, I want to make Grand Junction a go-to place. And to make it a go-to place, I need to have schools. I need to have education. So almost all of this stuff we go through, I have the fortune in this example to be able to put my one-pipe system in that's all under construction on the campus. Later, I'm going to show you converting a campus with a chilled water bill. Okay, so the story, we started geothermal about 2006, and we started looking at it. They wanted a lead badge is what they did. And so we go through, then we designed for a new classroom building. We built a geo field, and it's typical 100% geo, no extra stuff with it. And so we're going, and we get our lead points, all that. But about the time we get halfway through this, they start talking about, well, if it works on this building, will it work on a dorm? Well, sure, where's the dorm? Oh, it's right down there. And, oh, by the way, we're also going to build a science center and renovate that, and we're going to do the student union. Where's that? Well, it's all around the quad here. I said, oh, boy, hey, you know, hang this carrot in front of me one more time, please. We can use GX on the 6 buildings. We're getting ready to build a remodel. Yeah, we can. But what happens if we convert it over and decide to start using a community loop? What do you think of that? And the guy looked at me and he said, well, what would you want to do that for? And I explained to him that the students were one place or the other. Or maybe a third place, but one place or the other that pretty much on the campus taking classes or in the dorm. So I either had to heat, and in the dorms I'm going to heat, because this place has weather. In late June, probably 120 degrees. In the winter, -10. So anyway, so we take in this is all city campus right now, and you can see a shot of it. So we start looking at it, and this is what I would have to do. I had what I call a hairpin loop come up through the center. This is 2 18-inch pipes. Because we were told to design the builds off the campus, so we designed for a build out to 4,000 tons. So, and then these are laterals that will go off to these different buildings as they renovate them. And by the way, these are the dorm complex that they wanted to build at that time. And then this is the science center here, and here's the new student union, here's the classroom building that started the whole mess. And as later you'll see where we've got our boreholes that they're spaced around that. We also were told that any equipment that was in the buildings that had not reached its service life was to stay and be connected to the system. So automatically we got some of the boilers that were in the older guys, and we had a cooling tower, 500-ton cooling tower. Now think about this for a second. 4,000-ton loop, 500-ton tower. 4,000-ton loop, 500-ton tower. What would you, well, what's going to happen? Well, we say we did the calculations, and at least enough to keep the president awake. You know, he wouldn't, over a page, and he kind of drifted off. But anyway, he was just figuring out how to raise more money. Less energy consumed, reduced combustion and greenhouse gases, less water use. Drift and PM 2.5 is one of the most dangerous things we've got with cooling towers in cities. And I'm going to propose to you that evaporative water itself, a molecule, is polar. And I'm also going to propose to you that a hydrocarbon diesel fume emission is also polar. And what happens when we get a plus and a minus? We get black gunk on the top of our cars. You see it in wintertime all the time. These conditions are just right for all that to happen. So, but we're not going to breathe it now because we're not going to produce it. So, biggest benefits were when we combine diverse loads. We got dorms, we got student unions, we got hot water, we got all kinds of different things to play with. So, strategy one: recover wasted energy with a distributed energy loop. We talked about this loop: harvest it, move it, reuse it. So we started building. The backbone's an 18-inch pipeline. The mechanical room, the main mechanical room for this initial program is 20 by 40 feet, with a little bit of work overhead, as you can see. But in there, I housed my main system pumps and the heat exchangers to the cooling tower that I got out of this deal, the 500-ton tower, a boiler that existed, a chiller that existed. By the way, we used the chiller directly on the loop too, and stuff if we want to, and all of the metering and monitoring and corrosion, plus the fire riser down at the other end. So the first thing they liked was the amount of space it took, or didn't take. So, pipelines going in, there's 8-inch laterals and 12-inch laterals to the dorm and stuff. We do taper some of these 1-inch loops. All of this stuff are actually deconnected loops. So when I go back to this slide, each one of those laterals is a deconnected loop, okay, or a distributed energy loop, if you will. And so it means it's hydraulically independent. Okay, now we got going around the campus now, and look at all this stuff we can do. Just to give you a picture, the pictures of the buildings. Now this is 2006. We started out doing this, and we're moving forward. And that was the original loop that went up through the center of campus. And then we also turned around and designed a full-blown, once we started, we knew that we had demand recovery we could do. We started, because this is tri-state generation, and there's a big bonus for load shedding. And so particularly in the summer to get an event. Every time this facility manager punched a demand reduction button, this global demand, he'd get $5,000 to $10,000. Happened somewhere between 6 and 8 times during the summer. I don't know what he did with it. I never saw it in my budget. But anyway, but you can also see that we distributed the energy. There's the main. But this is the build out in kind of the next phase. We have a primary loop was here. This little deal here. We have a vault in the middle of campus that helps us balance the fluid. This is another primary loop, 18-inch. These are hydraulically decoupled and stuff. And then I've got the dorms as I'm starting to build west and a little bit more south again. This is a 12-inch loop that goes back in here, and of course it's independent. Some of these things have their own bore fields. They can be shut off. It's just like a water system. I can regulate it. Over the last 11 years, we've had one leak. Turned out to be an electric fusion coupler that was not properly installed. But we were able to isolate the loop into like 7 different sections and find out where that leak was. You go through every one of the buildings has shut-off valves in there. So we have a global demand. They all share the same fluid. There's no antifreeze, except where we have something on the roof. We have a heat exchanger with the main system, and we have an antifreeze glycol loop that goes to the roof. So you can see it's getting pretty complex. And we got pools to play with and some sports arenas. These are the classrooms that are on the system. Those are the main dorms that are on the system. But now we're moving west and south. We're getting more classrooms and so forth. And we're getting a little bit more room for bore fields. We originally programmed 250,000 feet. I'll show that statistic here again, but it's up. I think we got right at 200,000 right now, and we're, we didn't have, and so it turned out that the feet per ton we were using as we go through to kind of look at our thermal storage, it turned out to just get better the bigger the campus got, and a little bit less. So, single button campus-wide load control, load shedding at peak events. Second, reduce cooling tower water, reduce electric load. Okay? Well, originally, here you go, 3,400 tons was one of the original design conditions. It calculated water use of 14.5 million gallons a year, and the load to run the cooling tower transfer pumps and fans and everything else is about 784 kilowatts, almost a megawatt. With this district system, the existing system, I have a couple of old towers that we picked up along the way. I've got a total of 750 tons. We use 4.5 million gallons a year, 10 million gallon a year reduction at the site. And remember we got a corresponding reduction at the plant, and my actual load to run those cooling towers is 185 kW. So we are able to kind of accomplish that. So, and we haven't fired a boiler in 8 years. We did eliminate the combustion for the build. We do touch our domestic hot water boilers, so just so I don't get caught saying we've never used one. But we're going to 134A, and that's going to change. So we're going to get 165. So, you know, here's what evaporative water, power savings, and capacity. That's just the hypothetical annual savings for about a 2,500 total hour runtime. And as you well know, a well-controlled system, that might be fine, but in a poorly controlled system is probably double that. But that's just on the tower use. And boy, just general statistics, design tonnage now 4,400 tons, we got 2,200 connected, tower capacity up to 750, and we've kept the boilers that we're not using. So 2006, and here's what happens to the campus, and this is the president's vision. 2006, we had 3,500 students, 6 city blocks, you know, a couple of complexes. They had a Yankee football team, you know, everything else. 2017, we've got 11,500 students. We're up to 12 city blocks, and our district system is connected through that. And you'll see some statistics here about what happened earlier this year. Future, one of the things we've identified, we just haven't touched. I mentioned a future an irrigation system. We have to water the grass out there. So, and we are tied on to the last guy on what's it called, Colorado tailwater irrigation. That means they're taking water out of the Colorado River, circulating it around the city, and then what's left over goes back to the river. So, and then the college is the last guy on that one. So, anyway, we're looking at just initially. This slide was actually made the middle of last year. We were looking to have a couple of new boreholes because we had some extra square footage that we could use underneath a basketball court. We were looking at a central loop expansion of an additional 2,200 linear feet of 18-inch pipe. Okay. Maximum summer temperature for the loop right now is 86. His minimum weather is 50. We're up to 62. So what we can see here, what is happening to this system? How do we manage it? How do we manage it in the future? What's happening is we're getting more and more cooling load on that, and it's carrying through. Deep Earth, by the way, is 62 degrees, just now slightly above deep Earth temperature. And so we're starting to think about what do we do. So that precipitated contract we just signed this week to pick up the irrigation system as part of the central loop. And we're going to use passive heat exchangers and stuff. And because they were afraid that they would increase the water going back to the Colorado River and stuff, we're only allowed to use the water that's being actually used on the campus itself. So we're planning on raising the delivery temperature of that water by about 10 degrees. And what our horticulturist guys say is that we will probably have to pay the guys to mow the grass 1 month on either side of the normal start and finish time. So, and effectively, we're going to keep this campus green when everybody else's grass is brown, strictly by taking waste heat and taking another application for it and utilizing it with what we're doing. So these are cityscape programs. This is ideal stuff I'm proposing. Short-term thermal storage, just for those who kind of want some so deep Earth temperature 62, our TC was 1.42 or 1.24. You know, we started stuffing stuff in there, and the system capacity on all of the fields. If we were to take the hydronic mass of the fluid in the 18-inch pipes, all the buildings, everything else, the bore field, the U-tube, the bed assemblies, add to it the thermal capacity of the grout and all the bore, depending on what the thermal capacity is or what we did, and about the first 2 inches of the bore field, we will have 8,200 tons thermal energy storage. Significant shift. And of course, if we're going beyond 24 hours, we can go deeper into the field. So it was kind of our first attempt at beta systems, borehole thermal storage, and management systems. So Chuck Hammock's coming along and stuff. He's worth having up here to talk about what he's doing and stuff, because he's starting to talk about managing where you get your energy, when you get your energy. It's actually it's doing, and of course the new thermal conductivity test invented by Garen Eubank, Chris Clemenzi, and Galvin Liu. That if you read the papers in there, you see that we have potentially some real interesting stuff about what we can do about defining the characteristics of the bore field. And this is going to tell us a whole lot more about thermal storage. It's going to tell us about depths, optimum depths. It's going to tell us about what to expect down there. And effectively what they're doing with mathematics and statistics is doing what Slover J. does with drilling logs, electric logs, and the oil and gas business. This one I did just for John. Where is he? I saw him in here. There he is. Well, there's another John back there. Different John. 800,000 square feet. 3 years later, 1 million square feet. 1 megawatt range, heat. This is the introduction of the new library, the updated student center, and a new yard, all at the same time when the students came back. This is the updated first ones the previous year. This has not completely gone away, so we're after this guy right now. But we've been able to do demand limiting on this whole campus over with a 50% expansion in square footage, similar type uses, similar kBTUs per square foot, and everything else, and keep it at a 1 megawatt band. Okay, excuse me, does this big start to look at CHP? If nothing else, to get rid of these guys. And maybe give me another little bit of heat. I think this is one of the most, this is all the way, by the way, this gauge is all from Excel Power. 100 million 2 square feet on it, 16 buildings connected, 18-inch and 12-inch. Boilers, we save over $1 million a year. And it kind of is a swing thing because we put something new on, we have a little bit more energy, we get it up and we get it running, energy bills go down again, you know, and stuff. So we're going, but based on where we were, we figure we're probably about 3 million under where we were about 5 years ago. And then the global demand management becomes very valuable, and fully integrated building energy management is now planned. They finally, after this whole time, they would not let me put energy meters on the building so I could really tell what was going on, when it was going on. Last year they let me do that. So now I'm going to be able to turn around and go through this stuff, and we're going to be able to a whole lot more analytical, and we're going to be able to probably predict exactly what we need for device expansion, bore field, cooling tower, whatever, by analyzing that data. So,
what was their thinking for not putting meters on and measuring? Other than stupidity.
The CFO said, I've got so much extra money, I don't care. He's now retired. Not because of that decision, because he got too old. But that's what I was dealing with. I was dealing with a community college that was basically the whole board of directors were locals, uneducated. You're not. And so, but shall we say, just not this? These are not part of their vocabulary. Saying Grand Junction is an energy town, big oil and gas. So a lot of the stuff we're doing is kind of against the grain of what these people were brought up in. But as we started to show this to them, and we started to say, hey, did you notice our campus doesn't have a yellow haze over it? And stuff. And there are certain days when you can actually see that part. You know, they started to come around and say, hey, this is a pretty good deal. And we're just now getting to the point where I'm allowed to market. Second one, real quick. I've got about 7 minutes, so I'm going to do fast. This is Weber State University. I told you that we didn't have to have a single loop, that we could go into retrofits. This is a chilled water loop. Engineers, how much flow is a chilled water chilled water system size for per ton? Come on, Jim. 3 gallons per ton, right? What's a heat pump size for? 3 gallons per ton. Does it make any sense that I already have in place a central loop system? I just have to figure out how to manage it. It's already there, and this one's got tunnels. So I can actually walk along my steel pipes. That's up as we go through there. Weber State University, Ogden, Utah. So these guys are another campus that's just totally visionary. Okay, 2007 they signed on to the Energy Accord greenhouse gas inventory. They did all this. They wanted to be carbon neutral by 2050. Does that sound like anything you guys know about? Mm-hmm. Okay. And they're going to say we need carbon neutral, not emitting more carbon-based products. You have to then control them and clustered in other ways. So it's a balance. It is not net zero. So we go through there. Amoresco came in and did his thing. They did and proposed revolving energy, water, and this, that, the other thing. And the guys just looked at it and said, that's not where we want to go. You're not going to get there. All you're going to be doing is metering our gas and managing our gas. So they turned around, and at that point in time, there was a challenge put out to the managers of the facilities guys at campus. They said, we'll give you the dollars, or the majority of the dollars, and we'll seed it with $5 million to start to do energy upgrades to this campus. Okay, and they start moving along. And you're allowed to have everything else you save. Cool. So, well, they did all the good stuff. The way Jake, the facilities guy says, we put in the lights, we did this, we sold the pumps, we got the VFD done, but now here we are, and we're at the point where we've done everything we can do. Utilities are seeing this today, by the way. I mean, they were very successful at energy conservation with LEDs and everything else. They're selling a whole lot less kWhs than they were before. And all of a sudden, they figured out that wasn't profitable to do that, was it? So now we're going to look for beneficial electrification, but we got to do it right. So, but that question mark, that's that gap that can be filled by heat pumps and your HVAC system and other related devices. So, what are it? You see this goal before? Somewhere up around CMU, 2006. Optimize energy saving, minimize water use, recover wasted energy, distributed, reduce and cooling tower. Same goals, same strategies, different campus, different style of mechanical delivery. These guys did make a mistake, and I keep telling Jake that about guys who did this. He said some of the first changes they made were VRF. Now I have a driver building for my loop. I don't like that because I got to keep it above 48. Have to, otherwise you'll lose it. So we started talking to, it's so easy. Yeah, right. Look what it's doing to you. Here's what it costs to put this many extra boreholes in. Everything you saved on your VRF system went to ground. Anyway, Weber State layout, and I would say, meaning Jake, he said it was one of those light, you could see the light bulb going. Anyway, shift below, we're going to start to look about where we're going to be. We looked at the chill water system. By the way, these are zones that we have broken master plan of the campus into from the chill water system coming out of the central plant up here. And the stuff that you can see, the interconnection valves we've got in here for our Lego system. We got the tunnels where we got this in. We got all kinds of things. You see lights. We're out there drilling. We got they relamp their stuff, and they host part of the March Madness deal, up there. And the first thing that happened, they put in all daylighted LEDs, but the TV crews shut their crews down because it was too bright. So they had to make them de-lamp or go up and disconnect about every other lamp before they could film the games. So we started out on the west side of campus. We found a couple of places. This is right up against some hard rock. We did some thermal conductivity testing in some green spaces and parking lots across this campus from 2013 and started working on the system then. We did thermal conductivity testing, not too bad. Some places. Out in the middle of the campus where we were under the Great Salt Lake, the old basin range stuff, and so that's down to 1.17, not so good. Deep Earth's okay. So we're there. And then we began the first flexible bore field stuff went in and started going in 2015. Just the layout of the top parking lot, guys up there drilling, stuff. Gorgeous spot to go visit and take a look, and not too bad a spot to send your kids to college. Some of the stuff, this is down in the soccer field earlier, late last year, earlier this year. But, we're going through it. When we started looking at the bore field statistics, the ton hours and stuff on my upper field right now, I've got about 2,395 ton hours. And the lower field, I got about 2,500 ton hours. Stuff that we're already starting to build up. We only have two loop fields in across the whole campus. As we start in this. By the way, there's also another challenge from an engineering standpoint. There's a 600-foot elevation difference between the east side of the campus and the west side of the campus. So what do you think you have to worry about on your high-density polyethylene pipe? First, we have to start thinking about heat exchangers in between our stuff at the lower end of campus. So something different. Well, I mean, you're going to see this is me also. Let's see if that'll work. So this is the last field that was put in. Oops.
Cary, you do need to start winding down.
I'm 3 slides out, 4 slides out. Okay, well, we won't do that. That's a drone flight over the fields. Results and rewards. Electricity consumption down 29%. Natural gas consumption down 33%. Power bills reduced 40%. We fired our boiler, our main master boiler up there. We got some huge cooling towers and stuff. Last winter it was 7% of the previous year. And we started getting diversity in our central loop as we were checking it. In October, we were running 62 degrees still, without anything added to the loop. No loop fills, anything. That's how much load we were starting to pick up on the cooling on the new buildings, the glasses and everything. We're starting to measure what's going on. So it's neat. Energy intensity. This is an energy intensity. Of course, the red is the use of the energy and so forth before the central plant. Reduction in the bore fields, and the change in energy in the same 400,000 square foot group. There's a significant change in energy intensity or usage across the campus. And utility savings, we really came in right about here and stuff, so we got about 300,000 is what we're saving in energy with just 2 loop fields. I mean, it's not very big. 400 boreholes. Oh, that's it. It's doable, guys. Thank you. Let's have a drink. Questions?
Yeah, your question on most of these systems are campus-wide systems where you have control over the entire campus. In a community situation like Corona, do you have to integrate the control systems of the various different buildings, or can
We're talking about it, but generally we're still looking at livable environment. So their rules and regulations and conventions are 72 degrees and 68 degrees. It's pretty much the same thing.
But just
We hope you enjoyed this presentation from the NY-GEO 2018 conference. We would like to thank our sponsors, exhibitors, speakers, and attendees for making this such a great event. For more information on this conference, including speaker bios, presentation slides, great photographs, and more session recordings, go to our website at nygeo.org. That's ny-geo.org. Thanks.